Hi, my name is Nemutudi. I'll be presenting to you the work on adsorption of triazine collectors on spiralite 100 surface studies by first principle calculations. This work is in collaboration with people from CMR in Cape Town and also the Big Rim Group. Now, the purpose of this study is to recover spiralite mineral using different reagents and also to investigate the adsorption of novel triazine and their modification collectors on spiralite mineral surface. Why am I engaging in this research? This is to gain a first principle understanding of simple mineral to collector ligand interactions with a view to applying this understanding to the design of novel collectors, and also to understand better the reason behind the poor floatability of the slow floating spiralite. And what is the motivation behind this work? South Africa is one of the leading countries with highest percentage of platinum group metals in the Bushveld complex, which hosted about 75% of its reserves. And also, there is a growing demand in the industry of PGEs, and PGE supplies comes from mining and refinement of PGEs, which covers all minerals which contain PGEs as part of their crystal structure. Then what is the benefit that will come from this research? This is the reactivity of the collectors, that is the xanthides and other novel triazine collectors with spiralite, and this will establish an understanding in the chemical bonding and determine the best performing collector that will impact the mineral processing industry. So spiralite has been identified as a PGM which has a very poor natural flotation response. Therefore, new collectors are required to improve the recovery separation of hard to float spiralite. Possible reason for poor floatability. This is because of steric repulsion between arsenic lone pair of electrons and thiol sulfide, which results in lower binding energies. And this is according to Orison et al. And also, increasing pH results in the decrease of recovery, as shown by the table below. Now, we describe the methods and postulate used in this study. We use DFT method to investigate the interactions of collectors on the most stable surface. And the simulation that we used is Material Studio, which is a software, and a custom code. A 2x2 supercell for spiralite was also created and used, and we calculated the adsorption energies using the formula that is below there. Spiralite crystallizes in the isometric system with a para-type group structure, and a bulk structure was cleaved to a surface unit cell, and a surface supercell was relaxed, allowing all the atomic position to relax. The most stable surface, which is 100 surface, was considered for this study, and the surface was calculated to a value of 1.045 joules per meter squared. Now, checking the coordination of the various atoms changed after cleaving the surface, as shown by the below table. And the platinum to arsenide coordination for the bulk was 6 coordinated and reduced to 5 coordinated after surface cleavage. Then we adsorbed 3 different collectors, that is the xanthide, triazine, and triazine modified collectors on 100 spiralite surface, just to check the behavior as well as the bonding chemistry of the collector and the surface. And it was clearly shown that the xanthide and the triazine and triazine modified collectors prefer to bridge on the platinum and arsenide atom through the sulfur atoms. This also showed that the molecule with nitrogen binds stronger than the molecule with oxygen. Then, DFT calculation has been performed successfully to investigate the adsorption of novel collectors on spiralite 100 surface. Most importantly, it was found that the triazine collectors had stronger adsorption than the xanthide, and this portrayed to be a promising replacement of the xanthide collectors. And I would like to acknowledge with great appreciation the following parties, and thank you.